Okay. Good morning. So let's go back to where we were last time, which was so we outlined at the end of last class what we were going to see today. So let's recall where we were and sort of do the analysis of the discrete Poisson equation using things similar to what we see in PDEs, which is subharmonic functions as an auxiliary function. Okay, so we have the grid. This is our domain. Let's use a uniform grid. These are our interior grid points. Well, we have the boundary. And let's think of we have our 5-point molecule, okay, and we have our discrete Poisson equation. With the Dirichlet data. Okay. We already mentioned, right? So I'm not going to spend time writing this. I wrote last time. So L is our discrete Poisson. Okay, we have all regularity needed if we need to differentiate, and so on. Okay, still refreshing things from last time. I'm going to say that this is the exact solution, meaning this. Okay, the error. Basically the difference, let's see, it's Uij minus Vij. Okay, and we're talking about the local truncation error. So by linearity we have this. Local truncation error, Ij. We wrote the error. It's the typical error for say, Taylor polynomials. What else? So, yes, so those of you who want to check reference, I'm using our following. The book by Smith, one of our books that at the beginning you mentioned. Okay. Well, let me write it because I'm going to write an estimate, so let me write this. Okay, and therefore, from this, we can write that max over the grid of the local no, not this, for the error, sorry. We can write it like this. Okay, so bounded, fourth derivative bound by m twice, so we get this. So we're going to use this bound for the error, and let's see how we put this together to show that we have right, the order of the method, which is, as expected, h squared globally, right? This would be the local one. Okay, so it's a good exercise in things with numerical analysis. Yes, and I mentioned this theorem. I'm almost sure I did last class. I think I did sketch it. So we're going to use the following theorem. This would be in Portuguese, sorry. And so let me write it also without all details. So we have the uniform grid, we have everything. Okay, so let me write it in a simplified way from the notes. So let V be a grid function, okay? You know, we have the discrete Laplacian, blah, 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 everything as before. Grid function on this domain. Then we're going to use the theorem and then we'll prove it, okay? Then we have the following. The max of V okay, and I forgot to say, let's see, last time I didn't say this. Let's see in the notes maybe. It's a little bit, I might be missing this, but it doesn't matter. That we have our domain like this. Okay, I think I never mentioned this, and this is not, oh yes, it is, it is. It is in the theorem. Yeah, sorry. It is here in the bottom. Okay, yeah, it is. So it's not so bad. The notes, as I keep on correcting, not so bad. So we have then here just some function, right? It's a grid function on this domain, AB, this rectangle, and we can, for this function with given regularity, we can have this, this estimate. Okay, which then, look, if V was discrete harmonic, this would be a maximum principle for the discrete harmonic, and that's pretty obvious for the 5-point molecule. Agree? Because the 5-point molecule is always taking average of the neighboring guys. Okay? So that would be trivial. Okay, but so why are we going to use this? Because this is just a grid function, and we're going to use this estimate for the error. Okay? And the error need not be discrete harmonic, right? So this is what's going to happen. So let's first use this and then prove this in just a second using auxiliary functions so that we can get a subharmonic, discrete subharmonic function and not prove it, Smith proves it, but use the fact that a subharmonic function has a maximum principle, just like in the continuous case. Okay, so let's first let's use this result, sorry, handwriting bad. Let's first use this result for the error. So we're going to write that max here, max on the boundary. Okay, well, and here, again, already use, let me already put the result here, this result over there. So it's going to be m h squared over 24. Okay, already using this. Okay? But then admitting, so not taking into account round off errors, we can then cross this out. So exact on the boundary. Right? And there's a result for the discrete Laplacian follows. Okay? So the error would be bounded in this way. So we get the second order. Now, let's check the theorem. So back to the theorem. We're going to then show that this is true. This was just for some grid function, so this is good for some grid function. And in this case, we had, right, of course, the error, which is not necessarily discrete harmonic. Okay, so the proof of the theorem. So consider the following auxiliary functions. So let me even put a grid functions. That's always so the first one is this one, Fiat which will satisfy Poisson's equation in a useful way and has properties that we need. Okay, so this function, as you see, satisfies this. Okay. And we have two more auxiliary functions I think I can put here on the bottom. And these are similar to things that when we see some of these things in PDE scores, for example, Fritz John and so on, some of these guys appear in a similar way. So take these two auxiliary functions where n is defined as the max over the grid of this discrete guy, And Vij, as I mentioned, is bounded in a convenient way. Okay, so technical functions to do the job we need. Okay? So let's check now the impact of these definitions. On the proof, right? Definition, namely these functions. Okay, so the first thing, an important thing, is with these definitions of n, lead to this, that L of plus or minus Wij just one second, me speaking Português. Tá fazendo algum barulho aqui na camisa, não tá não? Ah, não tá não? Tô com a sensação de tá ok. Ok. Tá bom. So, this is equal to plus or minus L Vij plus n. But this is then, because of the definition of n, this is greater or equal to 0, right? Just look there from the definition, L of phi, right? As we saw, discrete operator, it satisfies Poisson equal to 1. And this then implies that V plus minus are discrete subharmonic functions on the grid. Okay, so let me do a little bit of a note. I know that some of you, or maybe all of you here present, have heard of subharmonic functions, but also to have this on the video, let me write down. Do you all remember what subharmonic functions are? Have you seen this, right? The PDEs course? So let me write it here to be complete on the video. So for example, say in Fritz John, we have the following. The book, right? We have that. If the Laplacian is greater or equal to 0, in the ball, that's or equal to rho. Okay, this could be even x in Rn, as we saw as there is in John. Then one has this. Area of the unit sphere, right? So remember this, if the function is harmonic, this is the equal sign, which is, right, the mean values are right at the center. This is the mean, which is the area of the surface, integrating over the surface, right, of the ball. This is what we've seen I think all of you here present have seen this in PDEs, right? And if the function is subharmonic, right, so a function with this property is called subharmonic. So this implies what this means. In the notes I wrote a little more, but right? Subharmonic in this sense, even though this is greater than 0. And it has maximum principal and so on, so, okay? So Smith and we're going to skip this part. Smith shows that in the discrete case, subharmonic grid functions also satisfy a max principle. Okay, so therefore, that means max of W plus minus on in the interior is less or equal than max on the boundary. Okay? And this will basically lead us to the proof. So I'm going to sketch, and you know, basically do almost everything. Sketch what's in the notes to save us time. So basically, what happens is the proof is that to get this, right, we use these auxiliary functions that leads to this guy being subharmonic, right? And then there's a proof in Smith, I won't do this proof, that then we get the maximum principle, and the maximum principle leads to the inequality we want. So let me just sketch here this little space I have here without doing everything. You can check it on your own. So note that this is positive. These guys are positive. So this will be smaller. Than this on the boundary, because that's exactly what we have shown. Okay. And this is less or equal, then we can split the two guys, because one is positive on the boundary. This guy here okay. And you see that this guy also being positive, this guy, I can pull it out here, right? It's smaller than this, and the result will follow. Okay, so check. Okay, so this is basically using our subharmonic. Then one part is positive break like this. This one will be, this is positive, so small, we sort of get the result. Okay, check this as a simple exercise on your own so that you 100% sure you followed the proof. Okay, so this is one way of proving then that the 5-point Laplace, discrete Laplace equation, right, converges using basically ingredients that sends us back to refreshing our memories with things of PDE theory, okay, and the tricks of using this auxiliary function. Now, let me talk a little bit about a boundary integral method for Laplace equation. So this is convenient sometimes when we have a domain which is a complicated shape. Okay. So there are many ways one could solve this. You know, with people sometimes, if they want to solve with finite difference, look what happens. If you want finite difference, this is going to be sort of a piecewise jagged sort of contour. In some cases it works if this domain is not too complicated and so on. But let's see a boundary integral formulation. So let me leave it. Okay, I'll leave it like this. But we're not going to use a grid like that. Okay? So we're going to end up having a grid that's only along the boundary. So basically we're going to transform this 2D problem into a 1D numerical scheme, right? Or basically, I'm skipping words. The proper way would say it as I was writing. I was thinking I would say, if I would say everything precisely, would be transform this 2D problem into a 1D formulation. Let me write it like this, right? And then do the numerical method. I think that writes better. I think this is a more proper way of saying it. Okay, so some of you students that are here did the PDEs course with me, so I'm going to repeat some of the material we saw because maybe not everybody saw it, and even if everybody here in the class has an idea, it's good to have it also on tape, right, for later on refreshing memory and so on. Okay, so how do I do this? So the starting point is take the Green's function, which is the log. So let me write the full notation, which I won't write it always like this, because it takes time. But it's good to write at least once. Basically log of r. So this is the Laplacian Green function. And more appropriate to say, let me fix this. Take the 2D, take the 2D Laplacian's Green function, because in higher dimensions we have the Green's function slightly different. And this means that using the notation, this generalized function that satisfies Laplacian G equal to the Dirac delta. Okay? Then we do integration by parts, and we get Green's identity. Okay, so Green's identity gives us the following. We have this. So this is basically integration by part, right? We see this in more detail. It's very straightforward, not difficult, using divergence theorem and so on. We can write this. We do this in the PDEs class. I'm not going to do it here. But okay, so this is just integration by parts And here, I haven't used any property of the functions u and v, just that they are smooth enough functions. Okay? So this is just integration by parts. Or divergence theorem with smooth enough u and v. Okay, but now if we use the Green's function, I'm sorry, there's something that fell in my eye. So now if we use the Green's function, I'll take v equal to g, okay, and a harmonic u. Then we get to what's called Green's third identity. Okay, so we get this expression where I have here the point xy, right? And we're integrating over the contour. Okay, so out of curiosity, I mean, I know those who did some courses with me have already seen this. Who has never seen this equation, this relation? So good, everybody has seen this, right? So the interesting thing here, important thing here, is that this, let me put a D here, and this, let me put an N here. Let me actually help that like this. And neu. In German it means new, but this is Neumann, right? So what does this say? This expression says that the harmonic function the value of the harmonic function inside is completely determined by the Dirichlet and the Neumann data. That's interesting. That's good news. And actually, we know that for Laplace's equation, I mean, we can't specify both of them. We can do, that's an exercise actually we do in the PDEs course, that you can't not impose the Dirichlet and the Neumann data as a little bit in the spirit of a Cauchy problem, right? We get into trouble. It's an ill-posed problem. Okay, here in this course, don't worry. For this course, that's cultural information. We don't need it. But what this expression does show us is that if we know the Dirichlet and the Neumann data, we don't need to solve Laplace's equation. The problem is that we don't know these two compatible data. I mean, there's a compatibility condition, which I'll mention in just a second, for this data. Okay? So we're going to try now by the boundary integral method is we're going to try to, if you give me the Dirichlet condition, I'm going to try to find the Neumann condition compatible with that Dirichlet condition, which has a functional relation, which looks very much like this. I'm going to write it now. Okay? Or if you give me the other data, I try to figure that out. And then, once I know a good approximation for both data, Dirichlet and Neumann, I compute this integral here numerically, and I know the value of my harmonic function anywhere inside the interior. How? Through the Green's function, right? That means x naught and y naught, for example, are on the boundary. So I can maybe call this, like, say, a point P0, and this a point P inside, right? And I do this, these guys, sorry, this guy and this guy has information of the points inside and on the boundary, okay? So I'm going to come back to this in just a second. Okay, so this is the nice thing about the Green's function. Okay, so now how do I get one from the other? Well, first I need to get a functional relation, because this is a guy inside and this on the boundary. So one can then take this point. Let me put this. So one can take this point here to the boundary. Right? We see a little bit of this in the PDEs course. You deform the boundary. This has a radius epsilon. Okay? So a little bit in the spirit of like when we do residues, right? Or actually we did this here in this course a little bit when I mentioned about the interface problem, right? The jump and so on. The proofs all have similar flavors, like the Plemelli formula and so on. Not exactly the same. Here there's no complex variables. But in any case, okay, this guy is like the real part of log z. Well, we take this to the boundary. Then we let epsilon go to 0. And if we do that, okay, when we let p go to the boundary, then we get the following formula. I'm going to write it again. I was going to get easy right on this one. No, but I'm going to write it again so we can contrast. We get this formula. Let me put it like this. P So let me explain to you. Sorry, it was like this so I can explain better. So this expression here has this result plus the result when the point comes from the interior and goes all the way to the boundary. And what does this say? This is a nice formula because it says the following. It has the three cases. Look, when the point Q, and I simplified notation, so Q is always on the boundary. Okay, so this is R is P minus, is absolute value P minus Q, the distance from P to Q. Okay, U of Q and du dn of Q, this is the Dirichlet data and the Neumann data because Q is on the boundary. Now this guy here, I can have it in three flavors. This flavor here is P is inside, so theta is 2 pi. Okay, here it is. Now, when P is on the boundary, like here, right? Or at a corner. Today my handwriting, my hand is lazy. I don't know why. So when P is at the boundary at a corner, theta is the internal angle. So the internal angle at a corner is alpha, right? Here it is. And the internal angle at the smooth part of the boundary is what? Is pi. Okay? So basically, it's a little bit, this, you can see this a little bit in the spirit. It's not exactly the same, but it reminds us a little bit of residues when you capture sometimes half the residue like this, or an angle, or inside you're getting the full loop around, so it's 2 pi, okay? Fine, this is just like reading the formula, right? Doing the analysis and so on, and keeping track of things. Now look why this is important. Because now I have here my Dirichlet condition, and my Neumann condition, okay? And if I have one of these conditions, I can find the other by discretizing this relation. How is that? So you see, and let me actually use at least the technical words that appears in an integral equation. This is an integral equation, right? Now it's an integral equation where if I give you the Neumann condition, I know this guy, and I have to invert an operator which is the identity plus this. Okay? If I know this guy, the Dirichlet condition, then this is a right-hand side to some extent. This is known, and I have to invert the operator to find the Dirichlet, the Neumann condition, right? So these are what's called Fredholm equations of the first or second kind. Okay, so these are Fredholm equations, and they're of the first or second kind. Okay, so now let's mention a little more, a few things in terms of solving this. Another thing too, excuse me, that I mentioned in the PDEs course, and here it will also just be a comment, is that from the terminology of electrostatics, so those of you who in physics, in some undergraduate course in physics, have studied electrostatics, this part here is called a potential, of a single layer potential, right? It's a potential because it's solving this with this sort of singular right-hand side. So this would be a single layer potential, and the Neumann condition is the intensity of this charge. It can be a positive charge or a negative charge, that depending on the sign of this function. And this here is a double layer potential. So the single layer potential, if it's a positive charge in electrostatics, we would see something like this. And the double layer potential, so this would be the single layer potential, and if it's a double layer potential, it's a positive and a negative charge that sort of collide. And this is how the potential looks like. This is a dipole. Okay? So this is just like physical interpretation of this relation. Okay? So therefore, here, if we go back to this formula, where we have the harmonic function inside, the harmonic function inside is given as a superposition of charges and dipoles. Okay? The intensity of the charge is given by this function. Right? So usually we write the Neumann data as a function g of q, and the Dirichlet data as a function f of q, right? These are the intensities of the charges, if it's positive or negative, and these are the intensities of the dipoles, right? So basically, we're representing a harmonic function through singularities on the boundary, okay? Why am I mentioning this? Because sort of just to connect words, when we saw the interface problem for the Kelvin-Helmholtz instability, we also had something singular, which was a vortex sheet over the interface, and we had something harmonic on top, harmonic on the bottom, and in that case, we were representing a sectionally harmonic, even better, sectionally analytic function, okay? So here, it's not exactly the same thing. We're not using complex variables, but again, we're using singularities to model and to simplify our problem. So basically, the important message of all this is that, which is something when I was a student, sometimes I would say, oh, this function is not so nice. It has singularities. It's bad, whatever. Well, sometimes actually singularities are the nice guys, the important things in the modeling, right? We think, oh, the function, it's not a nice property of the function if it doesn't have a derivative or this or that. No. Actually, if you know how to manipulate these things, they're actually useful things for modeling. Okay? So these are singularities. Okay. So let me go to that side and mention a few things, which then Master was asking to me in the beginning of the class about finite elements. I'm not going to be speaking of finite elements. I'm already starting to plan plenty of things to give you to read something, make a report, and so on. We'll see. I haven't decided what to give. But let me show you now what's called the boundary element method, which has a very sort of a kind of a close cousin to the finite element method. The spirit is kind of the same. So we'll see. Okay? Okay, so let me write that expression again here, just for the sake Q. Okay, so this is our domain. Okay, and here we have P and Q are on the boundary. Okay, now I'm just up to now just copying that formula over here, right? And therefore, theta. Let me just put it like this. Internal angle, right? Which would be pi if the surface, if the boundary is smooth. Okay. Okay. So how do I solve this now? Okay. So I want to find either u or du dn, right? I want to find either Dirichlet or Neumann. So let's solve this. So now let's let me summarize. A numerical scheme in the spirit of the boundary element method. Okay, so the boundary element method, the name sort of sounds familiar to finite element method, as you asked me in the beginning of the class before we started recording, right? But I'm talking like this. Sorry, because to record it so people on the video know what we're talking about. And usually finite element methods, right? You have usually finite element method, you do like a weak formulation of an equation. You have a variational principle, something I'm not going to show in this course, okay, at least here. So you have a variational principle, and there's strategies sort of minimize it, like weighted residuals, or if you have a energy principle behind it, in particular mechanics and so on. But the way you discretize this integral, right, the finite element method becomes an integral formulation, energy-based or variational principle-based, right? The way you discretize your integral, which is over the whole domain, is in the spirit that's very similar to what, at least polynomial-wise, as I'm going to mention now, as how we do it here, which is you take segments of your domain and you do a polynomial interpolation, therefore approximation of your solution in that subdomain. And this we're going to do here. But here, where I'm not using a variational formulation, nothing, I'm using actually Green's identity. Okay? So it's like mathematically we got to this point by a different path. But at this moment right now, as I'm going to explain, there's things that are kind of familiar to the other method, and that's why it's called boundary element, because you have this element. The element is this subdomain where you do a polynomial approximation. So that's why I'm going to sort of sketch for you now, okay? All right, so we're going to divide our domain. And this region here is basically my boundary element, right? Just like in finite elements, usually it's a little rectangle or a little, if you're doing in 2D and so on, right? You can do it in 3D too, finite elements. Okay, so now we need to do two approximations here. One will be a geometric approximation, and the other will be sort of a solution, a function approximation. You can think of it a function space and so on. So, right, even though we're not going to get into that. So how do we do this? So sometimes the elements can be called like this, notation delta K, right, which is that region. So let me do the simplest case. Let's see which one I have in the notes. Let me actually write the first approximation. So we use two, we call it type of approximations. One, which is of geometrical nature. That's what I mean by types. Couldn't figure out a better way. Geometrical nature, and the other one is for variables of interest, meaning Neumann and Dirichlet data. Okay, so the first two approximations. The first one, let me write it like this, is the geometrical one. So let me put it like this, A and B. So A, I'm going to write it like this. Where NJ I don't know why I put S. Is a polynomial that we want it to be equal to 1 at node j equal to 0 at nodes I different from j. Okay, and what does this do? So let's start this first with the geometrical approximation. So what this do is, because I have to do an integral, we have to do an integral over the boundary. So we have to specify our parametrization of the boundary. Okay, and if the boundary is curved, you might do an approximation as you wish, right? It depends on the problem. Sometimes you might do a piecewise linear approximation, right? Which means like this. That's how I did it in the notes. And by chance, my drawing is almost good. On purpose, I'm making it different. So this would be a piecewise linear approximation. I can maybe use it a parabolic approximation or whatever, which means what are the degrees of these polynomials? Okay? And usually we, that's why I put this C. Where did I write this? Well, yeah, sometimes I put it after. And usually C is a local coordinate, and C, say, can be from -1 to 1. The reason being, I mentioned this in the next page, but I think I wanted to mention that. The reason being because this can lead to, oh, my handwriting today, my hand is lazy. It's not even right. Gauss, Legendre, quadrature. So, do you remember what Gauss-Legendre quadratures are from courses you might have done in numerical analysis, approximation theory? This is basically, these are integration rules, right? We learn many integration rules. So I mentioned this when I teach here at IMPA numerical analysis, is that you want to do an integration. The first thing we think is that there's the rectangular rule, this most simple one. Then comes trapezoidal rule, that I used to think of it as a, well, okay. But after we learn alternate trapezoidal rule and spectral accuracy, trapezoidal rules sometimes, right, can be amazing, but it's a very good one. There's Simpson's rules. Do you remember what Simpson's rules is? Right, approximation by sort of cubics and so on, right? And off we go, right? All sorts of of integration rules, in particular when your domain is semi-infinite and so on. There's like Gauss-Legendre or whatever. There's many interpolations. Gauss-Legendre is an interpolation. Who remembers what is sort of a keywords? If you want to sell Gauss-Legendre, what does it has as its special properties? Yeah, well, it goes from -1 to 1. It's here, okay. It uses Legendre polynomials, and okay, you're getting there, but you still haven't said what I would say. What was it good about it? Well, it's not the minimum kind of error. It optimizes the error. We're getting close. Teamwork, very good. It looks like there's like this sort of TED group feel good thing. So we're getting there together. So it optimizes the error in some way, and how? What is it? Choosing the points, exactly. So I don't put my grid points wherever I want. I have to follow certain rules to put the grid points. And where are the grid points? At the roots of the Legendre polynomial. So it's a right, clever quadrature in the sense that I cannot put my grid points where I want, right? I have to put it at the zeros of the Legendre polynomial, and with that, I gain more accuracy, and I can integrate exactly, if I use n points, I can integrate exactly a polynomial of degree 2n minus 1, right? This minus 1, right? Getting old, my memory is failing, but I think it's 2n minus 1, right? I can integrate that exactly. So it's a very nice integration. So that is useful, that kind of integration is useful if I sort of know how my integrand looks like, right? If I have just data points, I can't do that. But if I have, and here I have the Green's function and so on, and the polynomials, right? So basically, when I substitute this, well, I'm going to use the same type of interpolation, right, for also the dependent variables, right? So the first thing is that by using this, I'm approximating my domain, okay? And this choice here is going to appear, let me just indicate it to you, here. Do you see what I'm saying? I was, let me take some water. I was very brief, I might say, right? But it's a good exercise. Why it's only going to appear there? Because basically, say, suppose I was using arc length or whatever to do this contour integration, right? This is actually in P and Q. Basically, I have to rewrite this, at least locally, into my local coordinates. So there's going to be a Jacobian that's going to appear here from the change of variables. And this Jacobian has to do with differentiating these guys, right? This is in terms of x and y, right? Our coordinate system. And then I have to translate this into local variables. So because I'm integrating from -1 to 1 and blah, 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 Legendre polynomial. So there's going to be a Jacobian, local Jacobian, which has to do with these guys differentiating with respect to the xi. So it's going to be derivatives of the polynomial, blah, blah, blah. Easy, right? Just work, but nothing deep. So this guy, these are going to play a role here. And then for the variables, the dependent variables, I do the same thing. I can do the same thing, but let me actually mention, I don't need to do the same thing. But let me write like this, and then I'll comment. Okay, so please, as I'm writing, sometimes I'm criticizing my own notation right from the notes as I've been mentioning. I would maybe, if I wrote this again, maybe, but it really doesn't matter because actually at this time of the course, when I'm talking to specialists and knowing, it's okay to write like this, or which one would you prefer? Or I could write this like this, right? Which means I'm approximating my thing by that. But when I write it like this, I'm basically already telling the experts I'm going to substitute this by that, okay, over there, right? So it's not, I'm leaning over the flag in particular at this time of the year close to election is not a very good thing. But this is basically saying that I am approximating it, right? And this tells us how many nodes I am choosing. This is the part I have to say. How many nodes I am choosing within my finite element. In this case, it's not a finite element, but within my boundary element, within the delta k over there. Okay? I'm going to draw. Let me exercise our minds first, and then I'll make a drawing to specify what I'm saying. So look at this. Let me ask you, do I need this j to be the same as this j? Think about it. Make sense of my question, which is not properly 100% well posed in the sense of, or else I give you the answer. What am I thinking? Can you guess what I'm thinking when I ask this question? So say it. More or less. So you're approximating, say, locally the space of solutions. I'm also approximating the geometry of my problem. See? You want to say something? No? No, it's okay. So let me help. So look at this. Look at this. The most simple boundary element I can do, and actually at one problem I tested, it was kind of okay, and then I just improved it a little more for my waves problem. This goes back to my PhD thesis. This was actually a method I used for the water wave problem and so on. Okay, and I'll tell you more if I think I'll have time. This problem has a little bit conditioning problems and so on. It can get the matrix that will appear can become ill-conditioned, but I was still okay, and I'll tell you why. Hopefully I won't forget. So this is what I did first. The simplest boundary element method. The simplest one is approximate the boundary by a straight line, and let me use a different color. I hope in the video the blue shows up, so I make maybe a very big thing. And I did this, look. So the blue, no, not here, sorry. This is the original boundary. It's here. So this is blue, and this is orange. Right? So blue is letter B, and orange, sorry, blue is letter B, and orange is letter A. So what am I saying? I am saying that basically for the geometry, I'm using two nodes. So I can do sort of a linear approximation of the boundary. But for my boundary values of the solution of interest, I'm only using one node, and I might call that a constant element, which means that the solution, be it the Dirichlet data or the Neumann data, I haven't told you which one I'm solving for, doesn't matter, right? But be it is constant over this, which is a caricature here. If I'm thinking of a piecewise constant approximation, I shouldn't make this guy big, right? Make it small. But so in this case, I'm using only one node for the solution of the PDE, but two nodes for the geometric approximation of the boundary, right? Which means my geometry here varies linearly, so it's piecewise, right? So the boundary will be something like this, right? Piecewise linear, but within each segment, my solution is constant. And if the solution doesn't vary very quickly, a constant here, a constant there, it could be kind of okay. If I'm using then two nodes, if J is the same here, and is equal to 2, okay, then I have two blue nodes also here. This is my element, and I'm saying that my solution varies linearly within that segment. And therefore, I will get that it is continuous at the node, right? Or else the other one, the constant one, it will be discontinuous at the nodes, but I don't see it because actually the node is here and the node is there, right? But over the boundary is continuous. But sometimes that's okay. It's just like when we approximate integrals Riemann, right? Approximation, it's like piecewise constant and so on. So those are the choices, right? And therefore, those are the degrees of, say, each element, right? And that's a little bit the spirit, a similar spirit of an approximation of when one does finite elements. The only thing is the mathematical setting of the problem is different. First, finite elements in this problem, finite elements would be a 2D approximation, right, with sort of little areas instead of little segments, right? But the polynomial approximation is the same, and if you learn basic finite elements, you very quickly start hitting this kind of parametrization so that you use Gauss Legendre approximation because the approximation is polynomial within each element. And then, of course, this is like finite elements that started in the 60s and so on. And we're now many years down the line. And there's all sorts of approximations. There's even spectral elements, which you do sort of a spectral type approximations within each subregion, whatever. I am not an expert. There's just a whole area just for that. So here is just a little mini tip of a huge iceberg. Yes, Márcio? Yes, let me repeat here a little bit the question. Marcel, is that actually, but you're saying these two polynomials, this polynomial being different from this one, right? Well, if this polynomial being different from this one is not so bad, because this one is mostly, I think, going to affect the Jacobian and so on, and as we approximate inside. You see, then when we do the Gauss-Legendre integration, our integrand is not polynomial anymore. So even if we put large n, whatever, choosing the number of points inside with the order of polynomial, we're never going to get an exact integration. But who cares, right? In life, rarely we get an exact integration. So this is going to be here. When I integrate, say, let me integrate this guy here. When I integrate this guy here, okay, this is going to be a polynomial, and this is a log, right? The numerical approximation of log. But, you know, you should test this and and see, right? If you have, in particular, you test it first for known solutions, right? And you see that you have a pretty good approximation for this guy, okay, using Gauss-Legendre. So I don't think it really matters. This one, over the diagonal, you're going to have a singularity, okay? But there are tricks. So you can compute this guy and so on in an interesting way using, for example, solutions you know, right? Then you compute this coefficient and so on. What I was going to say, yeah, but I think going back to your question, I don't want to leave it up in the air. We're kind of okay at time, is that if this polynomial here is different order than this one, right? We need these two to be the same guy, so we have information at the nodes. But this one right now, maybe I'm missing something, but I don't think there's a problem, right? For the geometry and approximating the geometry, and right, you could actually have even a curved geometry. If I'm not seeing anything mistaken, actually this is something I programmed decades ago. I haven't programmed exactly like this for decades. Is that you could even have, like, say, a curved boundary, right? Say you use 3 nodes and you put quadratic polynomials there, right? But over this curved boundary, your function varies linearly. So you just use the 2 nodes, the extreme, and so on. I think there should be no problem. Okay? So this is the spirit of boundary elements. Okay. Okay, I forgot, but here in the notes, on the next page, there's a little more details. I won't write this because I want to make a few comments as we finish the class. But you can read it. Okay, so I'm not going to write it. No, I might write one of them. Yes, I might write one of them. I think it's useful, yes. So let me do an integration over just one element. This is going to be approximated by this. Well, let me write and check something that's coming through my mind. Okay, where the Jacobian, I'm not gonna write it because it's pretty simple. So let me see if I have this right. Yeah, I think so. So check with me as I'm checking. What am I checking right now in my mind? I think it's right. It's like the I's and the J's where they're appearing. Okay, so this is just our boundary integral over only this guy. Okay. Let's understand the integration over only this portion, over one boundary element, right? So, okay, substitute this guy by the polynomial approximation, right? Substitute this guy by an integration from -1 to 1. So this basically here is an integration from -1 to 1, right? I'm just writing it like this, whatever. I could have written from -1 to 1. Here are the polynomials. Here are the Green's functions, right? Where, and this is the thing I was writing and thinking, where I have a pi here, which is the point where sort of the singularity of the Green's function is sitting at this moment, right? And the q is the variable that's running over the element, okay? So, okay. So we have the x's in here. Yes. And then look what I'm going to write now. Let me actually write and then do the comment. This will become a u which means Dirichlet data versus Neumann data. So let me tell you how I'm reading this, and that's why I was checking the I's and the J's. So the I is fixed here, and if I have things right, and the J is running from 1 to all the points in that element, right? But then I'll have the other points from the other elements and so on. So this I'm using for J, right? I'm not going to write this down. Maybe it is in the notes. I'm not even looking. This is like the J going from 1 to capital J is like a local number of the nodes, meaning this. So suppose I have like an element with 3 nodes. So it's an element that I did a quadratic approximation for both guys, geometry and variables. So in this representation here, this is J equal to 1. And actually, when you program things, you have to keep track of these things. J equal to 2, J equal to 3. This is like a local number, but this could be node 24, 25, 26, which is its global number, which in terms of really where it's going to go in the matrix. Okay? But this is just to simplify the writing. So this, look, if I'm summing over J, be it like this or be it like that, I'm summing over J, so it's I, summing over J over columns. This is like a matrix multiplication by a vector, right? Look at the vector J and the other one. So at the end, if I write that this, look, this, I put this guy here. If I'm doing one or the other, right? If I put this guy over here, well, I'm not going to erase because the integral is going to go wrong. So these two guys go together, and this guy goes together on the other side. Okay? So basically here I get a matrix multiplication. This guy, that will be a little piece of this. And this guy will be a little piece of this, right? Because I have the matrix, look, I have the matrix, say, B, right? So I'm basically doing like this part here over these nodes here, which represent that. Right? Can you see that? Feel free to say something, Lucas, in case. The I has to do with where the P, say the point where things are, where the singularity is sitting, for this case. Okay? So it could be inside here or outside. Okay? It's somewhere, of course, let's look here. It's somewhere around here. PI, or it could be in here. It doesn't really matter, right? I mean, it doesn't really matter in terms of just the formatting, right? So look, pay attention to this. So look, this part here is exactly the orange part of this calculation, right? This will be the coefficients that will arise from this, boom. And these are the vector entries that arise from here, right? So this times this is exactly either this or either that, depending if I'm talking about B or A. Okay? Now, okay, I have just a few minutes. Now, if I want to solve for Dirichlet data, that means I know the Neumann data. So I can either solve this equals this system equal to B, or this system equals to B, where B is my known part, right? Because I either know this or I know that because I know Dirichlet and Neumann. Okay? And what is the problem is this problem has ill conditioning properties and so on. And I just mentioned one thing, is that I had to do something similar to this for my water waves problem, because for water waves problem I have to solve Laplace's equation. I had to solve Laplace's equation in a domain like this, say with mountains in the bottom. So this was okay because I had the internal angles here, internal angles there. I could use this formulation, right? I would put this part here and this part here far away, so I had no activity. So basically the solution I knew it was 0 there, so this boundary I didn't have to worry about it, okay? But I had, as I was doing this on the computer at the time at New York University, which we didn't have a laptop, I mean, right? The computer, this is more than 30 years ago. So I had a condition number for my matrix that I had to solve, 10 to the P, where P was large. I think P was around, I don't know, maybe 8. Condition number is large, 8. And for various reasons, then I went to the John von Neumann Computer Center in Princeton, where my advisor had an account. When I was ready to do the heavy-duty simulations, I know my code was working. And actually, I decided not to go, I had so many things to check, I decided not to go after a preconditioning strategy, even though the condition number was high, because I was in a supercomputer that had a double precision. Remember I mentioned this for Krasny problem. It had a double precision of 28, 29 digits. I think maybe 28, which is 14 times 2. And 14 would be the double precision of usual computers. I think MATLAB 16, whatever. So I didn't have to. So here's a question which is, up to where I don't know if there's like a proof, but it's a sort of a practical rule. So why it was okay for me to have such a large condition number, but my solution was good. I did not see any effect of an ill conditioning since I was working with say 28 digits of accuracy. Do you know what happens, sort of a practical rule, if your condition number is 10 to the P, so let's take P, what is sort of the practical rule of accuracy? Is that, I don't know if you know this, but basically you're losing, more or less, P digits of accuracy if your condition number is 10 to the P. Okay? So if I am working with 28 digits of accuracy, and my condition number is around 8 or 10, I forget, it was big, I'm still okay. And I could see this in the computer. Actually, results that were bad on my desktop were good on the supercomputer, and it was not so much because the supercomputer was more powerful. No, it's just being more powerful, my code ran in less time, right? But when I did like baby tests on the university computer, it was not my computer. I didn't have a laptop there. It was very expensive. On the university computer, some results were bad because I was using double precision, 14 digits of accuracy. The condition number was 10, and I had 4 digits of accuracy only to my disposal, and I could see a little bit, not things going completely bad, but I could see the solution was like hairy, as I used to say to my students. We had little things going up and down, which was round of error contaminating the solution. And as soon as I ran that same problem on the supercomputer, it disappeared. Okay? So this problem, there are preconditioning strategies, blah, 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 and so on. But for this problem, when I was using a very, very accurate arithmetic, because it was double precision in the supercomputer, it was not a problem. Okay? For solving these guys, for solving a system like this. And actually, in my case, for water waves, that's the last comment I'll make. I already ran over time. The last comment is that for water waves, it was a mixed problem. Because, right, I already mentioned some of this, I think, in the class. I basically have a Neumann condition here on the bottom, which means that my bottom is impermeable, and I have a Dirichlet condition here on the top. And here, basically, I have nothing. So this matrix here was part A, part B, mixed, whatever. Okay, that's not too much of a headache, just organizing things and so on. Okay, so sorry for going over time, and I'll finish here.